So let's start with the session, and the session topic is RCNN and LSTM. So we will go through with it one by one, and I'll share the basics, and I'll discuss the basics of this terminologies with you, why we are using it, what is the application, how we should use it in Python also. So everything will be discussed. We need not to worry. So we know it that what is fully connected and other things. So we will start with basics of RNN, what is recurrent neural network, why we should use it. So participants are still coming, that is a little disturbing. So just wait for 1 more minute and then we will finish it off. So basically, the whole game actually, when we have discussed it also, the whole game was started for computer vision, image processing, segmentation, and everything. So what we are trying to convey over here, that why we are doing RNN, what is the role of INN. So as you can see in the screen, it is this is a fully connected network, fine, and it is very much clear that what is fully connected network, and we are having x1 feature to xn, like layers like x1 to xn. N is very large, they have considered, and growing this network would become too large. Now we need something else to get some efficiency in our own work. So we now will input one x1 at a time and reuse the same age weight. Fine. So the major reason why you cannot or we cannot proceed with the problem by building a standard convolutional network. So we have gone through with convolutional network, but this problem of building a standard convolutional network followed by a fully connected layer is that what is appearing on your screen, the length of the output layer is variable. Getting my point? So you can see it over here, the length of the output variable may vary. It may not be constant, or most probably it won't be constant. This is because of the number of occurrences of object of interest is not fixed. As xn is very large, so the number of occurrences of the object of the object of interest what we are doing is not fixed. So if it is not fixed, a naive-Bayes approach can be can be used for solve this kind of problem. So it will take a different reason of interest from the image, and they may use CNN to classify the presence of object within that particular reason. What we are getting at in a very short span of time, I'm getting into it. So the problem with this approach also is the spatial location, the different spatial location. That will always be your biggest challenge while you are implementing some of your work on CNN. That is different spatial location. So different spatial location, if I'm saying, it means I'm trying to say different spatial location within the same image. We are not considering different image. Getting my point? We are considering the same image, and we are considering the different spatial location in the same image. Fine. Now we have to, we would have to, rely over the aspect ratio if we are dealing with some images. So how the things has been started and how the things are getting resolved, everything will be there in RNN and RCNN and other things. So basically what you would try to do, you would have to select a huge number of reasons in this case. Fine. And this could computationally blow you up. This cannot be done computationally. So we need some algorithm to get it solved. So therefore, algorithm like RCNN, RNN, fine, yellow, and different other algorithm. I am not exactly remembering, but these are the similars we are having. So these have been developed in case of CNN to find these occurrences and find them fast. Not only to find the occurrences, it has to reduce the complexity and it has to perform the things very fast. Otherwise, it won't have any other specificity to go further with. So we have to get these two factors done by these things to detect those occurrences and to detect those occurrences at very fast rate. Fine. Then there is a case that what is RCNN, and I mean a reason with CNN feature. Reason with CNN feature. That is a one line answer. Reason with CNN feature. So what problem I have discussed with you in a previous session, like to detect a cat using convolution, using padding, using filter, and using fully connected network. These all 4 or 5 parameters we have discussed in a very basic manner. So you have to consider that particular example, whether it is cat, whether it is dog, whether it is duck, we don't have to bother. We have to bother about that whether we are giving object detection or not. If we are getting, doing object detection, so to bypass such problem, in this way these are approaching. Getting my point? In this way these are approaching. So these are, recurrent neural network we are dealing with. So recurrent neural network, how it is dealing with, how it is performing itself on reason-based approach, and how it is getting the best result out of it. What other algorithm which is, better than this? We will discuss it, thoroughly. So to bypass the problems of selecting huge number of reasons, fine, and to reduce the complexity, what it is showing it over here, fine. See how it will reduce the complexity. These are the functions, these are the input functions we are having. So there is a function of h and x as an input. Getting my point? Now we are having a different feature map, different function of different input. So we are getting it very deliberately. So no matter how long the input or output sequence is, we only need that function f are different. How function f will be different if we are using the same name? By their parameters, by their vectors. Fine. So then it becomes feed forward NN. That the RNN becomes feed forward NN. So this may be treated as another compression from the fully connected network. Getting my point? So this is the basic thing. And before prerequisites, you can see it in a detail, but it is a very complex thing. But the same thing has been thoroughly explained in this manner, in which we have taken a very simpler example and we have converted it into simpler form. How parameters are getting associated with the functions and how functions are dealing with those parameters separately. So if the function f are different, then it becomes a feed forward network. That is the underlying point. Fine. So this is another compression or fully connected network we can say. That's why I have repeated twice. This slide for this slide. So deep RNN again. So we are having some different functions. So you can see it over here. The parameters are also changed a bit. The dimensions are also changed a bit. That is deep RNN. And then the whole parameter has been changed. It shouldn't be same now, but the process is same. So you can see it over here. We are having input image. We have to extract the reason. We have to compute the CNN feature, and we have to classify the reason. That is RCNN is all about. That is deep RNN is all about. So to bypass the problem of selecting huge number of reasons, here we have to select huge number of reasons, right? So if we have to select a huge number of reasons, Ross Girschik was an author. He told that he proposed a method. He proposed a method in CNN, but he has also changed some layers and some filters and all. He has not proposed a full algorithm which can be applied to some other method by other authors. Fine. So he basically said, Dr. Ross had said that where we have used selective search to extract, when we have to extract the reason, suppose you have to extract n number of reasons. Suppose those n number could be 2000, 2 lakh, 2.5 lakh, 3 lakh, or anything else. So you have to extract just 2000 reasons from the image, and what he called them the reason proposals. So instead of trying to classify a huge number of reasons, you can just work with the 2000 reasons. Then again you have to rely over that array concept and everything. That array concept will let you know that how you can pile up the things, to pile up the reason of the images, and you can use it one by one. That's why I have said that you have to get the input image. That's why I have said you have to extract reason proposal. That's why I have said you have to compute CNN feature. Once CNN feature has been computed, fine, you can see over here that F1, F2, F2, and there are different features. We are having F1, we are having F2. So we are doing the things like that because we are on a practical approach. Theoretically, I can explain it to you. Fine. So these are the things we are having. Can you see over it? Just have a look over it. Okay. So on bidirectional RNN, we will come in the next slide. Just the basic of deep RNN, we are having it over here, and what output we are having. So we have to make sure of that. So suppose we have taken what we are at example where we have taken 200 reasons from the image. So these 200 candidates, now it became candidate. So these 2000 actually, this 2000 candidate reason proposals are wrapped in a square or in a array. I'm taking the word over here, a square, and fed it into a convolutional neural network, CNN again. That will definitely produce around 4000 or 4096 or something around dimensional feature vector. Randomly I'm saying it in a round figure. Something around 4000 dimensional feature vector as an output it will produce for sure. So that is not possible manually. So we have to rely on some algorithm which should be reach, which should be naive, which should be efficient enough. The CNN act as a feature extractor here. Fine, what we have seen before also. And the output dense layer consists of the feature extracted from the image, and extracted feature are fed into some algorithm, whether it is quadratic SVM, whether it is kernel SVM, whether it is any kind of algorithm which is revolutionized, which has produced some better results in the past. So you can use a basic SVM also, you can go for kernel SVM also, you can go for quadratic SVM also. So when you are feeding the things into SVM, when you are extracting the features and fed it into SVM, it has to classify the presence of object. Despite of SVM, you can take anything, PCA, LDA, but SVM is much better as far as distance vectors are concerned or neighboring vectors are concerned. That's why we can choose SVM for better result. So what SVM will do now is it will classify the presence of object within that particular image. Fine. Within that candidate reason, what we have chosen, what we have selected. So in addition to it, if you are able to understand what I'm trying to convey, we can add that predicting the presence of object within the reason proposal. What proposal reason you have made, you have to select the candidate in that only. We need some better algorithm. That algorithm also predicts 4 values. Just write it down. It will predict the 4 values, and the 4 values which are offset values to increase, as you can see it over here in parameters also. As you can see it here also. These are the functions. The values could be 3 to 4 or n number of values. So particularly those values are offset values. Fine, those values are offset values. Even if we are considering bidirectional RNN, this same process will be followed. So why we are relying on offset value? That is one of your question which must come into your mind. Why we are relying on those offset values? Just to increase the precision of bounding box. As you can see the bounding box in bird recognition, cat recognition also. So outside of the bounding box you need not to go through. Getting my point? So what these SVM or what these classifying process or what these algorithms are doing, these are predicting 4 values and those offset values, and what it will do, it will increase the precision of bounding box. I can give you an example to understand it more deliberately and to more thoroughly. Suppose given a reason proposal, you have given a reason proposal, and the algorithm would have predicted the presence of person, but the face of that person within that reason proposal could have been cut in the half. Then what will you do? Any answer for this? So if the presence of that person has to be calculated or detected or depicted, and what if that particular face has been cut from that particular image, there we need some offset values which will help in adjusting the bounding box of the reason proposal. So if it is the matter, if it is the game of bounding box, or if it is the matter of figure, or if it is the matter of numerical value, then there is no need of such kind of things. We are relying on offset values. So we have to compare the offset value only. Fine. So whether it is RCNN, whether it is fast RCNN, whether it is faster RCNN, whether it is any object recognition algorithm, any kind of object detection algorithm, whether it is post estimation, whether it is vehicle detection, whether it is surveillance method, the difference between object detection algorithm and classification algorithm is only that in detection algorithm, we try to draw a bounding box around the object. Agree with me? What we are doing in detection algorithm, we are making a bounding box. Where we are making a bounding box? Around that particular object of interest. Why we are doing it? Just to locate it within the image. Am I right or wrong? Am I going it right? Is it clear to everyone? Just to locate it within the image. If it is located within the image, you might not necessarily draw just a bounding box in an object detection case. There could be many bounding boxes if you have to detect an object, whether it is beak detection, whether it is retina detection, whether it is anything else apart from this. Fine, as you can see it in the previous session slide also. So there could be many bounding boxes. The single bounding box cannot make the things done for you. So there are many bounding boxes which representing the different object of interest. In previously what we are doing, same object of interest. Here what we are doing, representing different object of interest. So within the image, and what you would know now, that how many beforehand is getting done. So this is particularly the major reason why we cannot proceed with the problem by building a standard convolution network followed by fully connected layer. So what I have told you in the previous session, those models were the basic model, but they were having many limitations. What I'm getting discussing it with you. That's why LSTM or RNN or faster RNN or fastest RNN has been proposed. So basically, as you can see it in the slide also, the length of the output layer is variable always, even if it is fully connected network. So this is because the number of occurrences of object of interest is not fixed. This is the single answer what I got to find for you. If somebody will ask you that there are different reasons and why these are getting happened, the single answer is the number of occurrences of the object is variable and it is getting varied at each and every step depending upon the parameters and external conditions. So every time we are doing it, we have to normalize the data set. If we are not normalizing it, we are not getting the right result. Some images has been taken in dark, some images has been taken in very, bright light, some images having, very high density, some images is having very low density. So in that case only, you have to select the offset value that help in, adjusting the bounding box of reason proposal. Fine. So suppose you are having convolution network. You are having n number of convolution network. You are having n number of convolution network. This is the nav one, but this one will tell you a better picture. You are having n number of convolution network. You have to make these things done, and what I have told you, just to make it collected in a SVM, like a covariance matrix we are making. So there could not be possibility that we have to go for single bounding box. We have to make many bounding box, for the reason proposal or for the object of interest. Even SVM for different bounding box will be different. Every time we have to use that bounding box, we have to use it. This is the problem with RCNN. Whether it is bidirectional, whether it is anything else, this is the problem with RCNN. What is the problem basically? It still takes a huge amount of time, the first problem. It still takes a huge amount of time. The complexity will be increased for sure. Why it is taking time? Just to train the network, as you would have to classify 2000 reasons. Now we have considered 2000 reasons or 2 lakhs reasons. 2000 reasons proposals per image. That is a huge task to do. That's why a question was asked in a previous session. That's why CNN has been used. This is not possible in machine learning at all. The algorithm will get failed if such kind of intense task or extensive task will be given to their algorithm. They are having their limitations and we should respect it. Second problem, it could be apart by getting through these lectures, by getting through the discussions we are having. The second problem could be like it cannot be implemented in real-time system. This is the basic problem. This is the very big challenge. If it is not applicable in real time, there is no point in getting a right or good research in it. Fine, as it takes around 50 to 60 seconds for each image. How it is possible in real time? That's my point is. Somebody will say that my work is in real-time system. We have taken the images from these sources. We have worked on the raw data from this hospital data. But what about the timing? What about the complexity? And if your thing is increasing the complexity, if your algorithm or if your proposed method is increasing the complexity, why we should use your algorithm? That's my point is. That's my point is. The third point could be, if you are selecting some search algorithm, fine, which is a very much fixed algorithm. So we don't need any learning, at this stage. So this could lead to generation of bad candidate reason proposal. We are not selecting the efficient reason proposal and we are not getting the right result in a same manner. So it is very obvious that we are not getting the right result in that manner. Fine. So before getting into LSTM, I mean long short-term memory network, we have to finish it off in a better way. So I have taken this from one conference. So how it is listen, attend, and spell, a neural network of large vocabulary, conversational speech recognition, how it is getting done. It is done like face recognition we are doing. It is done like basic data set we are having. So if we are able to reduce the number of time steps, so we are going in a right direction. So it will significantly speed up the training. That's my point is. And if it will significantly speed up the training, then you are on the right direction and your result will be very much valid. Valid, not varied, sorry. And then the naive RNN, I mean, this is a high dimensional function. So y is getting computed from two functions parameter that is called h and x. So f is a function of h and x. Fine. So bias can be ignored over here. That's my point is. So see, we have collected this and we are doing addition. And what softmax is doing? It is doing the summation of the product. What we have done in previous session also. So that's all naive is doing. What is problem with naive? I have just explained it to you. First problem was time. So when you are dealing with time series, it tends to forget old information. That is a very severe problem. So when there is a distant relationship of unknown length, we wish to have memory to it. That's where LSTM get into picture. Getting my point? What RNN was having as a limitation, LSTM has got it as a feature. Fine. So vanishing gradient problem is the other problem we are having, which is almost the same. Vanishing means just to get eliminated or to get out from that particular place or to some covariance matrix. We are having no data now. It is just vanished. So vanishing gradient problem will say this one. We are having neural network layer. We are having point-wise operation there. We are having vector transfer. Then we are having concatenate thing. Then we are having copy thing. So the sigmoid layer output, what we have done in the previous session, between 0 to 1, determine how much each component should be let through. Fine, it should be precised. So what you have seen that pink X, I'm just moving my thing over here, just timing maybe, color maybe appear something else in your computer screen, but it is pink, light pink, so X get is point-wise multiplication. Fine, so we are doing point-wise multiplication and at the same time, what we are doing? Summation of those products. Fine. Now there is a concept LSTM. Why it has been approached? What is the point of using LSTM? So once we have done with RNN or RCN or LSTM, then we would be able to mix those both concept and say the things to you. Fine. So what is LSTM basically? So I have explained it: long term, long short, L for long, S for short, T for term, and memory. So long short term memory network. Why we are using this? It is an advanced RNN. Getting my point? How it is getting done, I'm just telling you that. Just have an idea with it. It is an advanced RNN. So forget input, it will ask it. Forget input. The sigmoid get determine how much information goes through. So whatever is required, it will ask and it will get the things done. That's why it is an advanced RNN. So the core idea is the cell that CT, as you can see it over here in the figure, it changed slowly only with minor linear interaction. So it is very easy for information to flow through it unchanged. So as you can see it, this CT equals to FT into CT minus 1, means N minus 1, plus IT into CT. I mean sum of products, what we have done before, nothing changed. Point by point multiplication, point by point multiplication. So these, for these operations we are having many gates. Fine. So this decides what info is added to the cell state. So C is for the cell state and how it is getting done. Fine. So output gate will control what goes to the output. Input gate will control what is coming from the input and what input we are having. Fine. What is sigmoid is doing? Sigmoid 0 and 1. So it is getting a switch. So vanishing gradient problem in LSTM is handled it already, and ReLU replaces tan H. Okay. So in that case, tan H will be replaced by ReLU. So that is the sigmoid function is all about. So how we are getting this done? These are the basic things. So if we are comparing it, then we have to know that what it is basically about and how we are proceeding it. Fine. So if we are talking about LSTM, so what LSTM is all about? First of all, we have to know about LSTM, that how it is working. So basically it is advanced RNN. And basically, as you can show in, I have shown you in the PPT that it is a sequential network. Fine. So it is a sequential network that allows the information to persist the thing. Fine. So it is capable of handling the vanishing gradient. I have just mentioned you, I have just discussed with you what is vanishing gradient. So it was all about proposed to solve this vanishing gradient problem. Fine. So a recurrent neural network is also known as RNN, what we have discussed just before. It's used for persistent memory, but it was not having memory by itself only. So what is the point in using it? That's why LSTM was proposed. Getting my point? So let's say we are having an example. Let's say while watching a video, suppose we are watching any video and you remember the previous scene. Or while reading a book, you know what happened in the earlier chapter. Fine. Similarly, RNN work, they remember the previous information and use it for the processing or current input. So current situation and previous situation and future situation can be synchronized. Otherwise, there is no point of using it. Fine. So in this manner, the shortcoming of RNN is they cannot remember long-term dependencies. I have discussed with you in the previous slide that they cannot remember the long-term dependencies due to vanishing gradient. So basically, we need to solve vanishing gradient. So LSTM are explicitly designed to avoid long-term dependency problems. This is an algorithm which is proposed for avoiding long-term dependency problems. Fine. So what is LSTM again? If we are asking, so we can explain it that it was designed as an advanced RNN, or it is a sequential network which is designed to avoid long-term dependency. So if long-term dependency is avoided, we can have a better result in that manner. And if we are still having problem in getting the better result, we can have something else, which we will see in the later slides. Fine. So this is a very basic example that before getting into the architecture of LSTM, this is a basic example that if we are dealing with, suppose some problem like reading a book, like going through a video, then these examples can be very much relatable with such kind of problems. So we do have this kind of issues. As you can see in the slide also, LSTM architecture if we are getting it. So just have a look at this slide, and I will forward this slide for explaining the architecture part. So in a meanwhile, you can have any question if you are having regarding this. Otherwise, we can move to the architecture. So this is a peephole LSTM if you're having it. So allows peeping in the memory. This is the thing we are having. Allows peeping in the memory. So naive RNN versus LSTM. So as you can see it over here, in naive RNN and LSTM, we don't have very much, difference apart from that memory thing. So we cannot have the previous info that can make the things changed. Fine. C changes slowly, as you can see it over here, and CT and CT minus 1 added by something. See it over here. So this is white, that's why it is not appearing to it. This is CT minus 1. CT is CT minus 1 added by something. C changes slowly. That's the main differences from naive RNN and RNN. So at high level LSTM, works very much like RNN. I am agree with you if you are thinking this, that at high level LSTM works very much like RNN. Here is what I'm showing it to you. Here is an internal functioning of LSTM. So the LSTM consists of 3 parts. What will make the things very much clear to you? What those 3 parts are, those 3 parts are shown in the image. The first part chooses whether the information is coming from previous timestamp or not. The first part, that is this is the first part. There is a X, there is a Y, there is a H, and there is a C, that is changes slowly. Fine. So what we are doing here in the figure also, if we are getting into this figure, if we are not on LSTM, I'm just showing you a better figure than this. See, H changes faster. So HT and HT minus 1 can be very different in that case. But here, C and CT minus 1 is almost same. This is the information flow of the thing. I'm just explaining you how information is getting flowed. And then I will explain the things to you. Just have a look. I'm just making the things stepwise, then I'll explain it to you. Fine. So this is something you can have, to understand it better, in a better way. So here is the internal functioning of LSTM network. What I'm showing it to you. The LSTM consists of 3 parts. I have explained to you. Fine. The first part is shown. The first part chooses whether the information coming from the previous timestamp is to be remembered or it is irrelevant and can be forgotten. This is the first classification we are doing in the internal architecture. That whether the given information is relevant or not, whether these are information or whether these are errors or whether these are noises, this has to be checked in the pre-processing phase only. That's what it is doing. The first phase, the first function of LSTM. In the second part, as you can see it over here, in the second part, what we are trying to do, the cell tries to learn new information. Fine. What we are doing here, we are trying to learn new information from the input we were having to this cell. So we are passing those information to the cell, and those cells are getting learned, or those cells are getting into learning phase, and that's why it is called learning and training method. At last, what it will be happen in the third part? What will be happen in the third part? I guess the cell passes the updated information of the current timestamp to the next timestamp and so on. So the information passing should be done by one. Getting my point? Now you can see it over here. The 3 phases, how 3 phases are getting done. This is the answer. This is the answer. Control, forget gate, whether it is has to be remembered or not, control input gate, whether it is relevant or not. If it is relevant enough, it should be go for updating information. If the information is updated, if the information is updated in the last phase, the cell passes the updated information from current timestamp to next timestamp, from current timestamp to next timestamp to control the output gate, from current timestamp to next timestamp. Getting my point? I guess this is clear to all of you. So these four matrix computations should be done concurrently. Fine. And then only the LSTM can be performed. Fine. So these three, part of LSTM cells are known as gates. What I have explained it to you. These are gates. The first part of gate is called forget gate, as you can see it over here. The second part of gate is known as input gate. You can see it over here. The last one is called output gate. We have not mentioned the updating information as process. That's why I have make it white. So it is not colored. So this should not be considered in the fourth step. It can be considered, it cannot be not, but it is the process. It is a mandatory process we need to do, but it is here I have depicted for your understanding. Fine. This is called peephole. Just look at the thing, how it is getting done, how the things are obtained. You just have this. This is the thing we are having. So just like RNN, LSTM also has hidden state, HT-1. Remember this one. Just like RNN, HT-1 is in a hidden state. Getting my point? I have moved my cursor here. So HT-1 represent hidden state of the previous timestamp. So yeah, is it fine? Previous timestamp. Just have a look. Previous timestamp. Fine. So previous timestamp. So HT is the hidden state of current timestamp. HT-1 is previous timestamp, and HT is the hidden layer of your hidden state of current timestamp. So in addition to it, LSTM also have cell state representation, like cell state representation. That is, I'm getting back to the previous slide, that is CT and CT-1. Here we are, CT and CT-1. Okay to all of you? So here the hidden state is known as short-term memory, and CT and CT-1 for previous and current timestamp respectively. So this is current and previous timestamp, CT and CT-1. Fine. So the hidden state is known as short-term memory. Fine. This is known as short-term memory, and the cell state is known as long-term memory. Fine. So this is referred to this particular image. Now you can have a better understanding how it is getting done and what is the role of this. Just have a look. We are using CT also, we are using HT also, we are using element wise multiply we have to perform. You can see it over here. So it is very interesting. It is interesting to note that the cell state carries the information along with all the timestamp, isn't it? As we can see it over here, the cell state carries the information along with all the timestamp we are having. So let's take an example. Why not we should take an example just to understand it well. Everything has been explained in this process. Just have LSTM information flow, how it is getting done. I'm just trying to promptly share an example. An example is how to understand LSTM working. How to understand LSTM workflow, how to understand LSTM information flow. So how to do that? Any answer for that? Suppose I'm giving you an example. I'm giving you a real-time example. Suppose we have having two sentences separated by a full stop. Fine. We are having two sentences, just like prepositions we are using. So we are having two sentences separated by a full stop. The first sentence is, Professor Mohan is a nice person. The first sentence is, Professor Mohan is a nice person. And the second sentence is, Professor Parul, on the other hand, is an evil or is evil. Or vice versa, anything else can be done. Fine. So it is very clear in the both sentences. In the very first sentence, we are talking about that Dr. Mohan or Professor Mohan as soon as we encounter the full stop. So we started talking about, Dr. Parul after doing that, Mohan talk. So as we move from first sentence to second sentence, our network should realize that we are no more talking about Dr. Mohan. We are moving from one sentence, Dr. Mohan is a good person or nice person, to the other sentences, Dr. Parul or Professor Parul is an evil. So when we are moving from first sentence to second sentence, our network should realize that we are no more talking about Professor Mohan. Getting my point? Now our subject is who? Some other professor who is evil, Dr. Parul or something XYZ. Here is a forget gate. As you can see it over here, you all know that what is forget gate. So here is a forget gate of that network that allow to forget about it. That's why forget gate we are using. So this is what we are having, forget gate. That's why I have to moving come and forth to make you understand it better. Fine. So the forget gate will, what it will do, it will allow the network to forget about the Professor Mohan, and let's understand the role played by these gates in LSTM architecture. So we are having forget gate, we are having input gate, we are having updating information gate, we are having output gate. So if we are talking about forget gate, so in that same LSTM network, the first step is to decide whether we should keep the information from the previous sentence or to forget it about Professor Mohan. So instead of sentence, you can use timestamp as we are talking in technical terms. So what could be the equation in that case, as you have gone through with it? So F equals to what we have done, A into X into U plus H into W. So we are having everything with us, all the parameters. Just perform it. That's what we are having with different coefficient and all. But we are having the same thing. We are having, always we are having the same gate. Remember, just have a look. To perform the same thing, we need not to bother about how it is getting done. We need to bother about how to approach it when it is getting done and what is the application. Fine. So suppose if we are having CT or CT minus 1. So if CT minus 1 into F equals to 0, that means you have to forget everything. So what is XT over here? Input to the current timestamp. What is UF is here? Weight associated with the input. What is HT minus 1 is here? The hidden state of the previous timestamp. What is WF is here? It is the weight matrix associated with hidden state. Later on, we will apply the sigmoid function. And when we have applied sigmoid function, the Ft into Ct minus 1, if it F1 equals to 0, we have to forget everything. If F1 equals to 1, we have to forget nothing. So it is basically 0 to 1 case. Fine. If F is equal to 0, we have to forget everything. So we are making the things like threshold values. Fine. So let's go back to our example, that what I have depicted over here in PPT. Or I have just told you that Professor Mohan and Professor Parul, The first sentence was talking about Professor Mohan, and after a full stop, the network will encounter Dr. Parul. So in an ideal case, the network should forget about Professor Mohan. That's my point is. As simple as that. Easy or not? That's it we are having. So that is having the get recurrent unit. So it combined forget and input into single update gate. Getting my point? So we cannot ignore update gate. It is very much necessary. It also merges the cell state and hidden state. So this is simpler than LSTM. Getting my point? But the result is not as good as LSTM. So there are many other variants too. That's what I have mentioned in it. So that's why I have compared also. Fine. So before getting into feed-forward recurrent network, we have to see that what is LSTM is all about. So we will see it. You just have to look at how feed-forward network has been made. So I'm just trying to show you that how it is getting made. Getting my mind? So before getting into it, we have to compare it with some other process and why this process has been used. That's my point. So this process has been used just to provide efficiency, just to reduce complexity, or something else. Fine. So if we are talking about the value, fine. If we are saying that, if the value also lie between 0 and 1, because this of sigmoid function only, we have to calculate the current hidden state. So we will use a new function, anything else it could be. It could be like ft, what is shown over the slide. Fine. So basically it turns out the hidden state of the function in a long-term memory, that is CT. Getting my point? So you can see it over here. CT is there only. You have to concentrate. Fine. So we are talking about CT. So if it is about current hidden state of if it is hidden state of the function of LSTM or long-term memory only, we are saying. So long-term memory is CT only. Fine. So if we are talking about long-term memory, it is CT only. We have to consider it. So you just, what research you are going to do, you just have to, go through with that particular process, and you just focus on these things, because these things makes the difference. Fine. So using softmax on Python or using some inbuilt function on Python will not make the things for you. That's what I'm thinking of. Fine. And I would like to suggest you also, in that case also, that what is application, what is all those things, that how we should use it. But the approach we have to follow, that how it should be used or how it should be implemented. So here in the figure only, the token of the maximum score of the output is the prediction only. We are doing it for prediction only. So this is more intuitive diagram of LSTM network. We are comparing it from GRU, but this is more intuitive and it is less confusion based. Fine. So this is what we were having in it, and apart from that, if we move to the next feed-forward recurrent network, we can have other things. But I'll share you that what is the application, how it is getting done. I will discuss everything with you now. Fine. This is high network. We have just considered it. We have just considered it to follow that we have to perform it, but it has nothing to do with the LSTM complexity and efficiency. Fine. So let's have a discussion over it, and I'll explain that why LSTM is better, and I'll explain that how to proceed with LSTM. Fine. even if it is highway network, what kind of network it could be, residual or a highway network, doesn't matter. Fine, input layer to output layer story should be same. Fine. So first of all, we have into highway network. So time series prediction, we are basically thinking of. Time series prediction is a different kind of problem itself for different type of predictive modeling algorithm or problem. So a powerful type of neural network designed, that's what I have explained, to handle sequence dependencies, means previous sequence is dependent on next sequence is dependent on next sequence. So previous sequence dependency is called recurrent neural network, RNN, recurrent neural network. But even those, the long-term short-term memory network or long short-term memory network or LSTM network is a type of recurrent neural network itself. Now getting the picture clear? It is the type of recurrent network itself, and what it is doing, it is used in deep learning basically. Fine, because very large architectures can be successfully trained, as you can see it over here. Not one, not two, not three, more than. So highway network automatically determines the layer needed. Fine. So in particular, this particular slide, you will discover how to develop LSTM network in Python. Fine. So how to develop LSTM network, for regression window and time step based framing on time series prediction problem. So this can be one of your tasks. The second task could be how to develop and make prediction of LSTM network and maintain memory state across very long sequences. This can be second objective, and these, trust me, these objective can make you done your MTech or PhD work. These are very, very challenging tasks. So in this particular slide, highway network experiment was what is saying. So grid LSTM is there. So we can develop number of LSTM for a standard time series prediction problem. In many paper you have gone through with this. The problem and the chosen configuration of LSTM network are for demonstration purpose only then if they are optimized. So if they are optimized, you can go for it. If they are not optimized, there is no point. So if I am comparing RNN, grid LSTM, normal LSTM, so a standard RNN fails to learn the presence of time tag greater than 5 to 10 discrete time step. That's where RNN got failed. That's where we have chosen LSTM. That's my point is. So the vanishing factor or the vanishing gradient or the vanishing error problem cast doubt on the whether a standard RNN can indeed exhibit significant practical advantages over the window-based feedward network. Fine. Or a recent model which is having short-term memory, which is having LSTM, is not affected by this problem. That is vanishing gradient problem. So LSTM is much better in this context. And it is not affected by this problem. Not only this, LSTM can learn to bridge minimal time tag. It can exceed, it was exceeding 5 to 10 discrete time step. LSTM can do 1000 time discrete time step. And they can enforce constant error flow through, constant error carousels. That is called CEC, I guess, if I'm not wrong. CEC. That is constant error carousels with the special units called cells. So we have discussed that there are two technical problems that was handled by LSTM. The first one is vanishing gradient, and the second one is exploding gradient. Both related to the problem that how network is getting trained. So it is basically solving training issue at the same time. Unfortunately, if we are talking about, you can see memory for both time and depth. You can see it here, time and depth. Just have a look over it. So if we are having this time and depth, so unfortunately you can see it over here, the range of contextual information that standard RNN can access in a practice quite limited. Fine, what we have discussed. The problem is that the influence of the given input of the hidden layer and therefore on the network output either decay or either blow up the things exponentially. So as it cycles around the network recurrent connection, this shortcoming can be corrected with the help of LSTM. That's why LSTM is very much important. Now, question arises that how LSTM works, and this is the answer. Whether it is grid LSTM, whether it is normal LSTM. So rather than go into the equation that govern how LSTM are fit, analogy is useful. For tool to quickly, get the handle how they work. What we are doing basically in LSTM, each memory cell internal architecture guarantees that no information should be flown or no information should be flow like information loss, or if it is not needed, we can forget it also at the same time. So the training system, the teaching model is very much efficient as compared to the other existing model. So 2 gates unit learn open or to close. And what they are doing, they are access to error flow within each memory cell. That is, I have discussed CEC. Fine. How it is getting done, and see how much complex it is, neural machine translation. So if it is LSTM, how it is encoding and decoding the things. So multiple analogies can help to give purchase on what differentiates LSTM from traditional neural network comprised of simple neurons. So we cannot compare it with the conventional neural network on basis of simple neurons. Fine. So we can have many examples. Now anybody can ask you that what is the sequence to sequence chat model that I have just explained to you, that if we are having encoder and decoder and Professor Mohan is good and Professor Parul is not good, or C is efficient or Professor Mohan is not efficient. So sequence to sequence chat model is based on that. And if somebody will ask you that what are LSTM applications, then what could be your answer? So this is an example of chat with a context. Why we are doing this if we cannot implement it in a real-time system? So it is important to get handle on exactly what type of sequence learning problem that LSTM are suitable to address. Sorry. So LSTM can solve numerous tasks. Fine. Which is not solvable by the previous things. And what were the previous things? That is RNN, Recurrent Neural Network. Fine. So these are the basic things we were having, but we are still having some issue. Let's see. Hello, hi. Somebody is unmuted herself or himself. Just try to mute himself. Let me do this. I'm actually not able to mute. Yeah. So screen is visible or not? Okay.
Participants, kindly mute yourself.
Please mute yourself, Pooja, ma'am. Yeah.
Yes, the screen is visible, sir.
Yeah, I'm sharing it again, ma'am, because some issue was there. I am not able to see it.
Okay, sir.
Yeah. So let me reach at the point where we were at. Yeah, what problem we are here with NAV RNN? What problem we are having? Just let me know. So when dealing with a time series, it tends to forget old information. We have discussed it. We need not to discuss it. Fine. So when there is a distant relationship of unknown length, we wish to have a memory to it. Fine. So we have discussed it also. That's where LSTM get into picture. So just have a look over it. Let me reach it. Naive RNN versus LSTM we have done. Peephole we have done. Feed forward network or feed forward recurrent network we have done. How it is getting implemented we have done, and what should we consider of while implementing it. Grid LSTM we have done. There is not much difference. Chat with context we have done. Speech recognition using RNN is a very classic example. So you must have gone through with this before also. So there is not much to discuss in that actually. But if we have to discuss it, we can discuss it in that manner. Fine. So my point is, if I have asked a question, now we can able to answer it. That what is difference between image segmentation and removing noise? I mean, we are doing the same thing according to me, but if you can add something to it, I would be rather happy to get something new from your side also. So kindly respond one by one. I'm hearing you. Um, am I audible to everyone?
Yes, sir.
Just let me know your answers. What is difference between image segmentation and noise removal in image processing, or whether we are doing computer vision in Python or MATLAB?
Participants can unmute yourself and answer for the questions.
You can unmute yourself or you can type your answer. Anything we can do. You can unmute yourself also. I'm hearing it. I'm waiting. According to you, what is image segmentation and what is image removal? Is there any difference or both are same? Both are doing the same thing. We have to answer. Actually, nobody can speak for half and
Both
two.
are
Both are different, sir. Sir, what is the difference? With all due respect, I'm just trying to figure it out. What is the difference, sir? Let me read some question if you are having. Anybody?
Sir, am I audible to you, sir? Sir, we can't hear you, sir. Hello, sir. Am I audible to you? Sir, am I audible to you? Sir, can you hear me, sir? Sir, can you hear me, sir? Sir, can you hear me? Am I audible to you?
I think there is problem at facilitator's end, sir.
Sir, Abhishek, sir, am I audible to you? Chat box போட்டுடலாமா?
I'm not hearing the facilitator anymore.
Is anyone talking? Sir, Abhishek, sir, am I audible to you? ம். Presentation இருந்தா- Sir, Abhishek, sir, am I audible to you, sir? You are not audible to us, sir. Sir, am I audible to you, sir?
Voice not audible, sir.
Sir, your voice is not audible to us, sir. Can you hear me, sir? Okay, sir.
Oh, am I audible now? It
Yes,
was
sir, you are
something
audible
in
now,
the
sir.
middle.
Yes, sir, you are
Yeah,
now.
yeah, yeah. It was something done in the middle. I didn't know. I was explaining the things. So my PPT has been done. If you are having any question, you can ask me. Please, and let me know if we can have a screenshot by. I mean, just on your camera, and we can have a screenshot together, if possible. First of all, you can ask any question if you're having. Please ask. Any kind of question is welcome.
Participants, if you have any doubt regarding this session, means you can ask the question to a resource person. You can unmute yourself and ask, or else
Sir,
you can put them in the chat box.
Yeah, some question is there. Yes, sir.
so that is feedback gate. I mean, is forget gate working alongside with punctuation. For instance, the example you gave, sir. So after the first sentence, if punctuation is and the second sentence follow, is forget gate working based on the
Sir,
punctuation.
I have already explained it to you. We have to make some threshold value. We have to go for whether it is value is going to be give zero marks, or whether the given value is going to give 1 mark. If it is going to give 1 mark, fine. If the city into a feature map or city into function is getting divided or getting producted in themselves, and if it is getting 0 mark, we have to forget everything. So it is not very much conventional. You have to go for what I am trying to say. You just have to make some threshold value, upper threshold value or lower threshold value. So if that product is getting at some value, just like association rule in data mining you have done, you have to eliminate that value. If it is getting upper than that value, you have to get that value. Eliminating that value means you have to forget that value. Getting my point, sir? Can you relate to association rule? Association rule is doing that they have set the threshold value, and above that they are not taking, or below that they are not taking. So that same concept will be followed in this case also, sir, in forget case. Even if you are using comma, even if you are using full stop, you have to train your model like that it will give some answer in that way. Am I clear to you, sir?
Yes, sir.
Okay, thank you so much. Thank you so much for asking. And you can take my email ID or contact detail. I'm open to research. If you are having anything to collaborate with me, I'm open to it. Thank you, everyone.
Sir,
If
there is
you could,
excuse
yes,
me, sir.
ma'am. Yes,
So
ma'am.
there is a one more doubt on the from the chat box.
Yeah, yeah, yeah. For emotion classification from spoken word or sentences, will RNN give better result? Ma'am, there are many other things which can give better result than RNN. You have to go through with it, because purely RNN, if it is getting better result also, what is the point? You should mix RNN with SBM, you should mix RNN with LSTM, and then make something hybrid. It will definitely give better result, Bharti ma'am. Don't go for the conventional thing. If you can club, actually I have not worked on that, but if you can club videos over it also, you have to make sure that the hybrid algorithm you are making, it should be used before on videos also. So SVM is used on videos also. I have used it personally. So you can definitely go ahead with that, ma'am. If it is a hybrid approach, it could be your personal work also. That's what I suggest you to go further with.
Any other doubt, participants?
Any other question?
Kindly share your email address, sir, please.
Yeah, I have typed it over here only. I'll just type it. I have typed it. Rest detail, ma'am or Anand sir will share you my PPT. So it is in PPT also. So you can connect with me. Thank you so much, Sudhanshu sir.
Yes. Thank you so much for interesting session, sir. Very nice
Not an
presentation,
issue.
sir.
Not an issue, ma'am. Thank you so much, ma'am. Can you share my? Can I share my number to them on this thread? Is it okay to you?
I will ask and then convey you, sir.
Okay. Saraswati ma'am, Sachi ma'am, please take it from. You can contact me on my email ID. I have just shared it with you. I'll share my number then. Thank you so much. My
Thank
one
you, sir.
request is if we can, switch on our video and then we can have a screenshot. Is it possible? I have to show it in my college also. Is it possible? Then please do it just for a while.
Participants to turn on their camera.
Yeah, I have.